Okay, hello students. Here I would like to uh, prove the learning target for today is y. So I'm going to prove y. The first is what is the reason why integral of secant square of x dx is tangent of x plus c. And the second thing I will prove is why secant of x dx is ln secant of x plus. And also we can prove this as tan of pi by 4 plus x by t. And then also I would like to show why these are the two things. What is the reason is integral of secant x is a logarithm of secant plus tan x, and can we write it in that form? And there's one more thing I want to show is why integral of tan of x dx is ln of secant of x. If you notice all the three integrals here, they do have secant, tangent, secant, and here again secant plus tan, and here tan, and so there is a relationship that you see between secant and tangent. So this is in the integral calculus, just the opposite of the differential calculus. So we do know that the first one is pretty easy. What is the integral? Is antiderivative, right? So antiderivative is the opposite of what you do. So we do know here y. So the first part is pretty clear by default. So the first one is by default because the derivative of tan of x is secant square. So it's quite obvious that the antiderivative of secant square gives you back tan of x. So that's straightforward, right? It's like we say, okay, the derivative of sine x is cosine x, and so we say integral of cosine x is sine x. So this is quite obvious, and the same thing we know for the derivative of cosine is minus sine. So that means the integral of sine x, only thing there's a minus there, so you have to write minus cosine. So these are the ones that we by default we know. So let's go back and see how do we do the second one. So we do know integral of secant square is tan x because derivative of tan x is secant square. So the main goal is to make this video is to understand what's the relation between secant x and tan x. How do we define? Remember the cosine of an angle for the circle with the center here, any point x here, and I'll take a unit circle. That cosine is always the x. This is the cosine, and that's the sine, right? So cosine theta is x, and sine theta is y. And if you see that, and the tangent is y over x, and the secant is there. I have already written down, so these two are already there. So my goal is to see what is, you see in both the denominators, they both have x in the denominator. And remember, you can't have x in the denominator. So when does the x become 0? And so you can see on the y coordinate, sorry, for 90 degrees, if it is 90 degrees, and you can see the first number is 0 and it is 1, and the first number is 0 and negative 1, that's cosine is 0. See, that's the x. So here x is okay. So this is cosine, right? So cosine. So it's for pi by 2. What is 90 degrees is pi by 2. So if I add another 90, so that will be total 3 pi by 2. Then you add another one, become 5 pi by 2. then another one becomes 7 pi by 2. So, so the so for x's, we should avoid all the so the x equals to 0 if the angle is pi by 2, 3 pi by 2, 5 pi by 2, and so on. So it is the odd multiple of like 1, 3, 5. You can, and not only just also with minus, right? You can also go clockwise, and you can say now odd number is always 2n is always odd, and just we add 1 becomes odd, a multiple of pi by 2, where 1 is all integer. So this is what we have to avoid. So the domain of secant and tangent is always any angle except multiple of pi by 2's. Now let's go with this background knowledge. Let's see how do we do the first one. So I'll start this secant of x, integral of secant x. Okay, so how do we do this? Okay. Yeah, it's so cool to know that secant and tangent are like husband and wife. They go they go together. There are a lot of formulas with this. Secant and tangent they combine because they have the same domain. Only thing, the range will be different. You can see the range for the green color is below -1 for the secant and above +1. And for the tangent, it's the whole. So look at the blue color. That's the tangent here. This is the tangent. It covers all the whole y. But the green one is below -1 and above +1. So everything except in between -1. Now let's go back. How do I do this? Let's see. So I'll do some manipulation, and that is, let me write secant of x multiply. So I'm going to do this and multiply secant x, and we'll see why do we do this, tan plus tan x, and I multiply secant of x times tan of x. So this will be I'm multiplying, so I'll put it in the parentheses. We use the distributive property. So let's use secant x to tan x. So using the distributive property, this whole thing will become, the denominator stays the same. Okay, so the secant times secant will be secant squared, and plus secant and tan becomes secant tan x. Okay, observe that if you see the denominator here, if you take the denominator, so if you take the derivative of the denominator secant x, okay, the derivative of secant is secant x tan x, and the derivative of tan is secant square, right? And you see, so if you take the denominator, you end up getting the numerator. So now, such case where if you have integral of f of x, if the denominator is a function and its derivative is up right here, and this we know from the earlier classes that this is nothing but ln of f of x plus c. See, so whenever the numerator is the derivative of the denominator is a logarithm to the base e f of x, and you can see this whole thing collapses to the integral of this is ln of the denominator. So that takes care of the first part. So how do we show the second part? The second part, we can write this as secant is 1 over cosine x, and tangent is sine over cosine x, and you will see that it has the same denominator. So I'm going to take this off, go back And this is same as, the denominator is the same, okay? And the top one is 1 plus sine x. Now I want you to use the by default formulas. This one, look at this. We can use 1 plus sine x. For the numerator, we can use 1 plus sine x is cosine x by 2 plus sine x by 2 the whole square, because if you expand this, you end up getting that. So we can replace the numerator as ln of x cosine of x by 2 plus sine of x by 2, okay, and the whole square. So this is square. But then the denominator, we can use half angle formulae. So the cosine has got cosine square x by 2 minus sine square x by 2, or 1 minus 2 sine square x by 2, or 2 cosine square x by 2. I'm going to use the top one. So this we can replace by cosine square x by 2 minus sine square x by 2. Then okay, so almost there. Now the denominator is a difference of square. A square minus b square is a plus b, a minus b. So keep the numerator as it is. But the denominator, there's a square. You can see this square, which is, I can write it this square is, so that's like, this is a and that's b, so you can write a plus b. So cosine x by 2 plus sine x by 2, so this would be 1, and then cosine x. Okay. Then you can see I missed once this square, right? And you can see this part, this is same as the bottom part, so one of them can cross it out. So there are two of those parentheses in the, so this crosses out. What are you left with is cosine x by 2 minus sine x by 2. I think this is plus because it is plus. Okay, so you get cosine x plus. Now this can be also divided by, if I divide each one of this, so I'm going to divide cosine x by 2, cosine x by 2, cosine x by 2, all this, it's ln of, this is 1 plus 10 cosine cos x by 2, 1 minus 10 x by 2, and this is by formula, look at this, 1 plus 10x and 1 minus 10x is 10 of pi by 4, which is 45. This is ln of 10 pi by 4 plus x by 2. You get that? So as I was saying, so easy. And then the last, one more thing I forgot is y integral of tan of x dx is ln of secant x. So we'll start with the left side. So if we start this in the left side, we can write this first of all. Tangent is sine over cosine, okay, dx, and you can clearly see that the derivative of cosine x is minus sine x, right? So if there is a minus, we need to multiply and divide by minus. So I'm going to write minus here and then minus outside, so that this looks like it is of the form integral of f prime of x, fx dx. We can write ln of the denominator. So this whole thing will be, by default, this minus sign stays. And This part is the derivative of the denominator. We can write ln of the denominator, which is cosine of x. Okay, so because of this minus, by laws of logarithm, we can write this as cosine of x raised to minus 1, where this cosine, because of this minus, we can write ln of 1 over cosine of x, and 1 over cosine is secant of x, because secant is secant is 1 over cosine x. So 1 over cosine is, so that's how we get this. Of course, I didn't write the constant of integration, but that's how it is. So this is what I wanted to show, how tan and secants are, they complement each other. So if you have integral of tan, it's logarithm of secant, or you can also write minus ln of cosine of x. So that also is correct. So both are correct, but you want to get away with the minus. So that's how it is because of the laws of logarithm. This minus 1 flips in the denominator, and 1 over cosine is 10. So as I said, this I did for tan, secant, and the next video I'm going to make is what about cosecant? So cosecant, integral of cosecant, and what about integral of cotangent? So I will do a video on that too, how you get integrals for that. So thanks for watching. If you like so the goal of this video that I make is, of course, we use this, but nobody checks how and where did you get this formula from. So it's always better to know why. So most of my videos will be why. I'll do a lot of proofs of this different even derivatives or integrals of the inverse or the polar functions, polar coordinates, and even anything that comes. I'm going to help you guys to make sure question yourself as why. So the inquiry-based learning is more important than getting full A plus. This is important. Why the heck this formula exists? Okay, so thank you. Bye.